Okay, so first thing is G, semi simple. Algebra over the field of complex numbers. Algebra. Then you have this positive roots, of course, Borel and R plus R lambda star. We have the linear forms and the integral, the weight lattice, and then the root system, the positive roots. Of course, with respect to B H. See. Now, I specify, and you have this x alpha, alpha positive, y alpha, alpha positive, and the H i's, standard basis. Now, one more notation. Rho is half sum of positive roots. So, take positive roots elements here, then add this in the lattice and add this half sum of then you have the W, the while group, of course, the while group acts on H and lambda also. So, the dot action of W on lambda. So, what does it mean? Lambda in. This is probably you can do it an H star also, entire H star, and then bring it to the restriction is stable for such that lambda is stable. So, lambda is an H star. What we mean by this? This is W of lambda plus rho minus rho. So, I add rho to lambda, apply W, then subtract rho. You can see this is an action. I mean, you just leave it as. If we need it, we can do it in the action tutorial. This gives an action W on star. Yeah. Now, yeah, this is one side. I am going to use this action to study this. Yesterday, I just so now I recall that we have the epsilon center of QT. Universal, and this is the universal enveloping algebra. This is the center, and we have this we saw yesterday that there is a chi lambda. So, okay, I fix lambda also. Chi lambda from epsilon to C homomorphism of C algebras such that z operating on b lambda plus is chi lambda z b lambda plus. So, b lambda plus maximal vector of weight lambda in z lambda. So, z lambda will be recalled in z lambda. I can write somewhere here, just z lambda So, think of one dimensional representation of the linear form through B, B as H. So, this lambda is a linear form on H. So, I can give a one dimensional representation and the unipotent, the nilpotent part, the x alpha kills that. So, that way I get a one dimensional representation and then I induce it. So, that is Z lambda that we have discussed yesterday. So, take a maximal, there is a unique maximal up to constant, non-zero constant, there is a unique maximal, and that this scalar operates by a scalar. That we have seen, because the center, that this details I think we saw yesterday, right. Should I recall or I can proceed, because there are more things. If it is not clear, I can do it. Somebody has why this is true, or can I proceed to the next? Okay. Now, look at this this Z lambda notation. This is just some notation. Don't worry if it is in the book or not. Just I am because of the character, I am just using that notation. So, this all those V in Z lambda such that Z times V is phi lambda of Z V for every Z in the epsilon. So, on the entire I mean, I take all those vectors for which Z completely operate on this chi, the same chi lambda. You see, now the claim is that Z lambda chi lambda is the whole of Z lambda. This is what we are going to prove. Okay. And why is it? So, the first thing is, let V be in the left side. Then, and let Z be in the thing, also let X be in G. Now, X times V, consider this, and Z times this X times Z times V, because the commutator is 0, I mean the center, it commutes, but this is nothing but X times chi lambda of Z. So, which is same as chi lambda of Z X times V, which means X times, which means Z lambda chi lambda is UG stable. Right. So, this is UG stable. Note that V lambda plus belongs to Z lambda chi lambda, which means UG V lambda plus is contained in this thing, but of course, this is same as Z lambda, because this is cyclic with a maximal vector V lambda plus. So, that is inside here. So, therefore, that is equal. So, the claim is proved now. Okay. Now, I use this to prove the following lemma. So, the lemma is the following. Let lambda be a weight is such that, I mean integral weight, such that lambda plus rho is dominant, lambda may not be. Here I have to spend a little time. Lambda may not be dominant. For example, lambda plus rho, lambda comma alpha I for some simple root may be minus 1. So, what it shows is, that is lambda alpha I, okay, I use the hi notation, lambda of hi is bigger or equal to minus 1 for every I. It could be minus 1 also. Then chi of lambda is equal to chi of w dot lambda for every w in the while group. So, I say that these two characters, I mean, has homomorphism, they are same. That means, for every z they are same, for every z in epsilon. Okay, so, let us give a proof of this. Proof is by induction on length of w. There is a length function on the while group. So, I use that. There is a reduced expression, take a minimal expression. Okay. So, if length of w is 0, there is nothing to prove. I start with 0, because if I start with 1, you could see the proof when I go to n plus 1 is same as the. So, I do not want to repeat it. If I do it here, then I will leave that as an exercise. So, I do not want to do that way. So, therefore, I can start with index 0. But then what is that? That means which implies w equal to identity, therefore, w dot lambda is same as lambda, and therefore, they are same, there is no problem. So, otherwise, choose a simple root, alpha I such that S alpha I w, the length is 1 less than the length of w. You can always choose radius expression, because otherwise, okay, because otherwise it is 0 if we can't push it. Okay, fine. I hope I can use such things, right? That length of, if it is not positive, then there is a, okay. Now, here there is one simple root, okay. The S alpha I mean the reflection corresponding to that alpha I. Now, look at this Z S alpha I w dot lambda. I mean, there is a bracket here, but there is nothing but it is same as S alpha I dot w dot, because I told you it is an action. So, but anyway, that is not, we are not going to use that. So, look at this one. Now, we have this consider. So, from here you can see that S alpha I w dot lambda of h I is bigger than or equal to minus 1 by, I mean, you could see from here, this is bigger than or equal to minus 1. The same idea of what I told, that lambda of h I, same idea, okay, for the same I. Now, if S alpha I w dot lambda of h I is exactly minus 1, this is almost the same case, which means, which implies S alpha I w dot lambda is same as w dot lambda. So, we are done by induction. What I mean is, therefore, this implies chi of S alpha I w dot lambda is same as chi of w dot lambda, but by induction this is a smaller one which is same as chi lambda. So, we are done by induction. So, we may assume So, we may assume that S alpha I W dot lambda of H I is bigger or equal to 0. Oh, sorry, there is a small, let me have to do a little carefully here. S alpha I W of lambda plus rho minus rho of H I. So, this is bigger or equal to C. So, what I am saying is if S alpha I of W of lambda plus rho. So, this is a dominant weight, this is only bigger or equal to minus 1. I think I wrote correctly, because this is dominant. I mean, what I mean is this is positive with alpha I. For that alpha I, that is positive, not dominant. For that SL2, for that alpha I, this is non-negative. Okay, but it could be singular. I mean, what I mean is this alpha I could be 0. Then that is why I wrote bigger or equal to minus 1. That is correct. There is no problem. Same idea. But now here. Suppose that is why I said, suppose this is exactly minus 1, that means if S alpha I W dot lambda of alpha I H I is exactly minus 1, then you say S alpha I W dot lambda is same as W dot lambda. Then I am done by induction, that I wrote the proof. So, otherwise we may assume, that this is non-negative. Sorry, this is this is non-negative. So, which means say call it M. Then y alpha I to the power m plus 1 of that V S alpha I W dot lambda plus in Z S alpha I W dot lambda is a maximal vector. Vector of weight lambda minus m plus 1 alpha I. Si of say W dot lambda, how? Whatever the weight minus m plus 1. This is the lemma that I proved yesterday, the last lemma. That is if lambda, I use a different notation, replace that by lambda. Lambda H I is m non-negative, then y alpha I to the power m plus 1 V lambda plus is a maximal vector in Z lambda. Okay, that is what I am saying. Okay. Now, so which means now you have this Z W dot lambda to U G, so call it V1, some vector V1, just for a confusion, I mean, to avoid confusion of notations. So, this V1 is a vector here. This V1, and we are in that module. Now, the thing is like, this is the nice thing about this module. The standard cycle, among the cycling is I mean, it is like free module in some sense. Like in the case of, I mean, if you have any finitely generated module from a commutative ring, from free module to that you can always push. That way, this is in that sense it has the property that if you have a maximal vector in some other module with weight equal to this weight, then there is a homomorphism of UG modules, G or UG modules. Surjective, which taking V w dot lambda plus 2 V 1, that cycling to this cycle by the. Therefore, now we are done, because what is the thing about our this z lambda chi lambda is same as z lambda. So, this z, any element of the epsilon, acts by the same scalar throughout the entire module, not just one weight, okay, entire module. Therefore, this here whatever the same scalar is here. But you see, by for this module also the scalar is chi w dot lambda, but for this module chi s alpha w dot lambda. So, that is the same. So, we are done. Any question about the last part? I mean, why they are same, okay, by induction. So, these two are same. By induction, this is equal to chi lambda. Therefore, those three are same. Okay. Now I am going to state Harichandra's theorem. Let lambda mu be 2 elements of H star. Note that what we have done there is for lambda elements of lambda, the integral weights only, but here he is doing a more general limit for anything. But finally, whenever the thing that we are going to use is only for fine dimensional irreducible representations, therefore, we should assume lambda and mu are integrals finally. But anyway, this theorem is true for any two, such that then what can you say about this? So, then there is a W in W such that mu equal to W dot lambda. The theorem. So, that we have proved that if you take 2 lambda and mu having that property, that is, this is lambda and mu, then they are same. That is the other way. If we start with 2 lambda and mu, they are same, then mu equal to w dot lambda. Okay. So, before going into the proof, let me recall some one theorem, and I state 2 lemmas without the proof. So, first theorem is that Poincare-Bicot basis. So, we have this fixed and ordering of positive roots. For example, you can choose you can do it in many ways. You can choose the longest element of the while group, choose a reduced expression, take the positive roots made by negative in that order. For example, one choice. Now, then so you have this x alpha in that ordering. So, and of course, H I you can order in any way, because finally this is a commutative thing. I think I do not have to worry too much about the H I part. So, you have so you can take this product of y alpha, alpha positive, some I alpha, product of H I over A I into n, product of x alpha power j alpha, alpha positive. So, these are all non-negative integers, I alpha, A i's, A alpha, non-negative integers, and I write in this order and then again there is an ordering here. I mean, I used already fixed a ordering of positive. So, in that order, again in that order, okay, is a basis of G. So, there is the theorem. So, such a basis is called Poincare-Birkhoff basis. Now, and then there is one more lemma that which if I have time, I will prove it today, otherwise we can do it in the tutorial. So, let consider this ring C H star, which is actually sim of H, which is also same as U of H, because H is abelian. The universal algebra is same as is a symmetric algebra, and there is the coordinating of the dual. Now, let lambda and mu be two elements here. Then there is a such that the W orbits are disjoint. It is empty, disjoint. The useful action, I put a dot, I should not put a dot, there is already here, but you can also do that. Now, there is a, which implies, I mean, if that is happened, then direct is the F is H star such that F of okay, there are two F's actually. There is a okay, so there is an F such that also W invariant is that F of lambda equal to 1 and F of mu equal to 0. It is a separation of points. So, intuitively, I mean, to make a little small remark, the H star mod W is again an affine variety. I mean, the statement is just to say that H star mod W is a quasi affine variety. In the sense, if you are given 2 points in a variety, there is a function which separates. So, that is why. And of course, this is mod W. Okay, so this, if I have time, I will, otherwise we can do it in the tutorial. G invariance of UG is precisely center. Intuitively, that's all the elements in UG commute, so the group in that sense. Okay. So, what is the action? So, G acts on the G algebra G, therefore, on the universal Elfing algebra, and the G invariance is precisely the center. Okay. So, I use these 3 of them. Again, at the end, I do not completely complete the proof. One small thing is the non-commutative and the commutative rings. There is a confusion. So, I don't get into the details at that point. I stop some point where again there will be a gap in the proof, means I do not want to for time reason and then. So, the first thing is to okay, so we will now proof of the theorem. Step 1 is I just construct a map from UG to UH, but of course, this is same as CH star. The map is given by phi of product of h I to the power a, okay, P is only a linear map. Linear map. This is same as so this identity, and phi is phi of any other basis element goes to 0, because if I know a basis element, then I can do it extend it linearly, and I know what is the basis. So, anything not involving that will go into itself, and involving that some kind of a characteristic function. So, this is so now I leave it as a small exercise, that which is not hard, I think is true, that restriction of P to epsilon is a homomorphism of C algebra. This just use Serre relations. I mean, those things you can push it, and then you take one of them and then multiply with another. You take the terms and then push it this side. It's in the center, so you can do that and such thing. You can do. I mean, because it's in the center, you can move it, and then of course that h times v alpha I is equal to minus alpha I. Those things have to be used to push it this side, and or without using such things also, we can see conceptually also, I mean, without doing that also, because what we have finally take an element here, z, in epsilon. So, z acts on V by chi lambda of z. So, we fix a lambda. This way. Now, in particular, so that I mean, of course, we have the highest weight, the maximal weight vector. But you see here, look at this part. If something is involved in this part, you take you write z as a linear combination of these things. You take a term of this part. Suppose there is one j alpha which is positive, that will kill V lambda plus. Okay, that's the first. The word is starting from here, so that will kill it. So so whatever involves this will be useless. Okay, for that purpose, unless chi lambda of z itself is 0. Okay, then this is the good one. Suppose something is, I mean, something here is involved, then that will push down the weight to something smaller. So that will not go into the same way. And I'm using that u minus, probably I notice now immediately, that u minus I think is linearly dependent on V lambda plus. So I think it's crucial to work with only z lambda and not V lambda, if I'm not very correctly. I mean, I thought it's true for V lambda, but it's not. So ug minus, I mean u minus, it's only at the level of, because otherwise the linearly independence will be spoiled. And anyway, so this shows that the only the h part of z will contribute to chi lambda, which means we have z, in other words, that is same as chi lambda of z is same as lambda of phi of z. Because the phi is that homomorphism, only the h part. Here I have to be a little careful. So when I mean lambda of h1, h2, I think of lambda of h1, lambda of h2. I mean, lambda is only a linear form on H. So, this is a kind of reason that this is a polynomial, and instead of thinking a symmetric element in the H star, that is a polynomial in H star. So, it is nothing but that polynomial at lambda, that is the meaning of it. Lambda is a vector in H star, and an element in C H star is a polynomial in, I mean, it is a polynomial function on H star. Therefore, that way is the meaning of that. Okay. So, this also tells you that this is a homomorphism, because that comes from chi lambda and P is a P and then lambda, that way.
Maybe it's better to say only the pure H part.
Pardon? Pure?
Yes, only the pure H part of that.
Yeah, you mean the one?
One with only H.
Yeah, one is, yeah. That's a constant function. Constant function is, yeah.
So, what you mean is if there is any X involved or Y involved, that part is.
Yeah, that's correct. Yeah, the part, that's correct. Okay. Okay, but I use this to, so this is one, and well, let us call some number. So, this is number 1, which I am going to use, and this is the first step. Say maybe this is the end of the step 1. So, now step 2, I just first thing is I have eta from C H star to C H star, sending H I to H I minus 1. So, HIs are linear forms on H star, because H star whole star is H. So, they are linear functions here. So, and there is a basis, and therefore, there is a polynomial ring with H I is an algebraic basis, lambda with phi to get another homomorphism of Z. So, psi psi of Z is, so this is first eta and then, eta of phi of Z. So this is one homomorphism, and now the claim. This is the step 2. The claim is psi of epsilon is contained in the W invariance. This is the claim. Okay, so how do we prove that? First thing is, to prove that, what I do is let lambda be, now this point, let lambda be integral, and look at lambda plus rho of Hi minus 1. Probably the Rao one's comment is coming there. Lambda plus, this is lambda plus rho of Hi minus 1. I mean, 1 is the constant. I mean, as I think of 1 as the constant polynomial function on H star. That is the meaning. So, minus 1. So, this is nothing but rho of Hi is 1. So, I get simply lambda of Hi, because rho of Hi is 1. So, this part, therefore, but you see this, think of this Hi minus 1 coming as eta of something, but you see eta is an automorphism, not just at the linear level. So, this shows that lambda plus rho of any, I mean, instead of this you could think of also for the phi of so lambda plus rho of psi of Z, so which is nothing but lambda plus rho of eta of phi of Z. Eta of phi of Z. but then the phi of z is coming from h part of thing. Okay. But eta is like hi minus 1. So, then that is equal to lambda of phi of z. See, because the eta is the twist minus 1, and then I could ignore and the rho, and then I get lambda phi of z. I mean, intuitively, a small checking is needed at the algebra atomospheric level, but this is true. Lambda phi of z. But what is this by 1? It is chi lambda of z by 1, chi lambda of z. So, what we have done is lambda plus rho of psi of z is chi lambda of z. But no, I know, can I write here? So, it will be very clear to see also. So, here chi w dot lambda of z, because now lambda is integral. You have assumed lambda is integral here, therefore, chi w dot lambda of z is same as chi lambda of z. This is by the previous lemma. So, these two are equal. But again use instead of lambda, use w dot lambda and then get into something like that. So, with this nothing but chi w dot lambda. I mean, I am not using special about particular lambda, any integral weight, this is true. So, in particular w dot lambda also I can do that. So, plus rho of psi of z. I mean, the whole thing. But what is w dot lambda? This is nothing but w of lambda plus rho minus rho plus rho. So, I ignore that minus and plus. I mean, minus rho plus rho. So, ignore, and then this is of psi of z. So, which means, what does it mean? So, just use here. So, this entire thing shows that psi of z takes same value at lambda plus rho and w lambda plus rho for every lambda. This is what we have arrived at. Psi of z, the polynomial, of course, for every z, takes the same value at lambda plus rho and as well as w of lambda plus rho. But what is that? You can ignore rho. Okay, you are in a group, additive group. So, what is you can think of that as mu and then w mu. So, therefore, that takes value on a constant value on each of the w orbits, but then only on elements of lambda. Okay. So, that is what I have observed. So, it says that, so what is shown is that I just recall, just to say it in a different way, that the polynomial, I mean, for every z in epsilon, the polynomial psi z takes constant values on each w orbit of elements of lambda. It's a small thing. When I read Empress, I just noticed, I thought that it's wrong. I mean, something it comes from linear, but it's not linear. The point is, lambda is Zariski dense. That should be quoted here. Lambda is Zariski dense, but that exercise is of course there. Yes, Zariski dense in H star. H star is an affine space of dimension equal to the rank. So, this is Zariski dense. I mean, something like you could think of Z, let's say, the complex number. If you take any intuitively, take any polynomial which vanishes completely on Z, it has to vanish completely. Therefore, it should be a 0 polynomial. I mean, you can do it for any Z, any number of copies. So, fix one variable and then do by induction whatever, and then you can arrive at it. Okay, so this is Zariski dense. Now, therefore, this implies that is invariant. So, what I do is I take one point and another w times that point. I mean, I take a f and w f, I mean this is call it f, w f, the difference will vanish on each of them. And therefore, on the Zariski thing you can. Anyway, so that is now that so this is the thing. Now let me come back to the main part of the proof. I mean that, so you have start with lambda and you will start such that chi lambda is same as chi mu. Now, chi lambda of, so I use that chi lambda of z is same as chi lambda of z, the first one. By the v of separation lemma, I call it separation lemma, points invariant separating orbits, the invariant functions separating the orbit, disjoint orbits. And this part I do not prove, I mean I do not do any more thing on this part. Intuitively I say, I mean there are non-commutative and commutative things are something there which we need if I have time at the last lecture or something we can do that, I will look at also. The thing is, this is, you ignore the dual, then the CHW is CG upper W. So, we ignore the dual, then CHW is CG upper W. And there is no much of a, I mean it is not any anything wrong in doing that. The reason is because H is isomorphic to H star via the restriction of the killing form and as a W module also. So, that is same as that one. I mean same means isomorphic, but this is same as CG upper G. And then the G invariance of UG is epsilon. So, except for UG, that part is epsilon in that sense. I will look at carefully because I was concentrating on next other things like constant partition function and Postel's formula. So, then I will do that and then if need I will try to. So, before going to the next thing, now I think I have some time to do that small thing, that CH star upper W. So, if I have two elements lambda mu in proof of separation lemma. So, suppose these two are such that W lambda is empty. Now, consider this. So, for every W lambda, look at the maxima ideals of this thing, maxima ideals, the intersection, plus M mu is the entire because this maxima ideal cannot contain the intersection, because if it contains the intersection, it should contain one of them, but they are all different. So, but then you can choose an F and a G, which is 1. Now, look at the orbit, the product. So, this is completely 0 on the entire orbit here, but this part you can take 1, 1, 1. So, that will be, so G will be the function which takes 1 here and then 0 here. That is invariant. The product of, what I mean is, product of these so that will work. Okay, so now we are interested in, so aim is to understand or study the character, okay, let lambda be a dominant weight, character of this model to the H. So think of V lambda as H model. So that will be some sigma m mu f mu. So has an element of z of lambda. So the mu's are in. So here mu's are in lambda. Of course, this is a finite linear combination because V lambda is a finite dimensional model. So this is a finite sum of this thing. But to understand this, they use certain composition series from z lambda and then use this. So that way we need to understand the character of, formal, okay, of z lambda, because it is an infinite dimensional thing, but the sum will not be an algebraic sum here, but it will be infinite, but each multiplicity, each multiplicity by Poincare Birkhoff weights or basis or anything, that you can see that there is a finite. And more important is why to study character. That's why to study character, because even in the finite group theory, the character has some information about the group. So that way, it's very important to study the character thing. Also, combinatorially, it's interesting to do that. Okay. So before that, so they are elements of z lambda. But to work with that, it is not sufficient to work only with z lambda, but we need infinite sums like this. So we introduce some sets of set of all functions on H star whose support is contained in a finite union of sets of the form. That's right here. So of the form lambda I minus form some finitely many number and lambda is the dominant. Finitely many. For example, our z lambda, the weights of z lambda will have that property. That even that fixed lambda, that will do that. So what do I mean by, so it's a function, it's a map from that, yeah. So, the multiplication on z lambda, so I can extend that to such functions. So, this way. So, let f be in this and be here f star g of lambda is equal to sigma f of lambda 1 g of lambda 2 lambda 1 plus lambda 2 equal to lambda.
This function, this thing, just to, this was introduced also in the first lecture. I just wanted to make a comment saying that this was also introduced in the first lecture so that they can make the connection.
Oh, the z lambda.
This x was introduced.
Oh, it's introduced already.
No. You go ahead and introduce in your notation. I'm just making
notation
the
is also the
just
same?
telling them. No, the notation was different.
Oh.
But the same thing appeared also in the previous lecture.
Oh, good, very good. So, he is saying the notation is maybe notation is different. I follow some place.
That's fine. But
That notation, yes.
But it needs to. I was just
But
pointing out.
okay, fine. But the thing is introduced already. So, up to that part, f star also?
No.
Oh.
You go ahead. You please go
Okay,
ahead.
fine. So, it's also good that if it is done also to recall. I mean, only thing is without introduction it should be bad. Okay, anyway. So, f star of g of lambda is, so I take the sums and then if it is lambda, go to the value. So, f of this and then g. So, this you can see at the level of z lambda, if a function is coming from z lambda, I mean think of that as an element of z lambda, then this is the multiplication here in the group ring the same as the, note that here there is a small thing that I have to say that E of mu into E of lambda is E of mu plus lambda. I mean, do not confuse, there is an addition already here, there is an addition here. So, that is multiplicative, that is a basis. Z lambda, the elements of lambda itself is a basis. Lambda itself has a basis, so let us not. Okay. So, this one, and now I have special elements like this one. You take epsilon lambda as a notation belonging to this. The notation is epsilon lambda of mu is equal to 1 if mu equal to lambda and 0 otherwise. So, this is this one, and we could see that epsilon lambda star epsilon mu is equal to epsilon lambda plus mu, because the sum should be 1. So, it should be 1 here or there, and then I mean both should be 1, because otherwise that becomes 0. So, that way. Okay, now the coming to this and note that epsilon 0 unit element. I mean the one like the one in the ring. So, that corresponds to the 0 element of the lambda, that basis element. And so now I introduce this notation, this map P from P in a thing. So, that P has the property that P of lambda is the number of sequences K alpha positive. So, this is inside Z non-negative, alpha positive of non-negative integers such that sigma k alpha is minus lambda. minus lambda, not plus lambda, and P same thing with plus lambda, a number of sequences of non-negative integers such that this is equal to plus lambda, that is capital P. Capital P is the genuine thing. I mean, of course, there is a connection, they are the same. I mean, you could do that minus, I mean, that thing. So, just to illustrate one example, we have this Dirichlet diagram SL3. Yeah, you have time. So, alpha 1 plus alpha 2, the root, you take this to be lambda. Okay, they take lambda to be minus alpha 1 plus alpha 2 because I am doing this one. So, take the negative root. So, this has two sets like this. So, take k, I mean k alpha 1 to be 1, k alpha 2 to be 1, and k alpha 1 plus alpha 2 to be 0. And then k alpha 1 equal to k alpha 2 equal to 0, and k alpha 1 plus alpha 2 to be 1. So, these two are, this is one sequence, this is another sequence. There are two sequences having this thing. That has some meaning. I mean, that is the dimension of the Cartan subalgebra of SL3 is 2. That is what it says. SL3, dimension of the Cartan subalgebra is SL3. I mean, even though I have written combinatorially, that has a meaning of that. Okay. So, now let me have one more function. So, f alpha, this is alpha is positive. So, that function is f alpha of k alpha is 1 if k is non-negative integer and 0 otherwise. Okay. Of 1 and f alpha lambda is 0 if lambda is not of the form. Yeah. Somebody asked a question? No. Okay. So, this one is yeah, and that part, and the negative part of that is now you have the so that P, the capital P is the constant partition function, and now you have the while function. This is the while function. Q product of epsilon alpha by 2 minus, okay, I have to be very careful here. This minus alpha by 2. I hope the notation is not confused. Sometimes the notation confuses so much than the mathematics. I mean, so alpha by 2, this is another, this is an element of H star, it's an element of H star. But now it is not in a lambda. I mean, it may not be in lambda unless it may be SL2 or SL2 alpha by 2 is omega, otherwise, okay, so this is, so this one, alpha by 2. Now, the Q, yeah, now we have some lemma involving the functions of the p, small p, f alpha, epsilon alphas, lambdas, and q. We have some formulas. 1. So, you can take first thing is that P epsilon 0 minus epsilon minus alpha f alpha is epsilon alpha is epsilon 0. Third one, q star epsilon minus rho is product of epsilon 0 minus alpha positive. So, and the fourth thing is so q star p is epsilon rho, and then the fifth thing is w of q is minus 1 to the length w. First, I have time, I think. So, and also there is one more. So, these formulas, we can do these formulas. Is that everything correctly written, or there is no mistake? No, in the piece product and this. Pardon? Star is okay. The multiplication I have written already product here. That means it is star. Okay. I mean that's fine. The star is the product here. Yeah. I mean if you want, that's a notation. This also star, but star means the product is the thing. So, here also this means, I mean if you fix an ordering of the positive roots, that is f beta 1 star, f beta n star. This is a notation, some order. This is the meaning of that. Yeah, okay. Let us spend time on the proof of these things today, the rest of the time. So, let us see the first one, proof of 1. So, look at the right side. Of any lambda. If lambda is not in the negative part of there is the coefficients of positive roots having less than or equal to 0, if we cannot write it that way, then clearly it is 0. And that side also it is 0. So, there is no problem. So, I can assume very well that lambda is in minus z positive roots. So, then if I take any, so that follows more or less from the definition. Yeah, sometimes the very standard things is difficult to explain. So, the lambda will be, so you have, so you take one partition m, I mean k alpha equal to minus lambda. Then each of them on this part it is 1 1 1 1. So, that contributes a 1 there. So, that way this is same as P log, because by the definition of f alpha that contributes only on those. So, the product is 1 only when each of the thing has to be non-negative integral value coefficient. So, this side also. Anyway, so here it is simply the usual power series kind of thing, that you have epsilon minus alpha. Here it is epsilon 0 plus epsilon minus alpha plus epsilon minus 2 alpha plus etc. So, the f alpha is like this. So, this is same as epsilon 0 square, which is epsilon 0, and then the rest of them, this is minus epsilon minus alpha. This is, yeah, this is a minus alpha. This is minus epsilon minus alpha, and then we get that. So, only term, the first term remains, other things the alternating that get cancelled. Okay, so this is a formal proof. The third one is this one. Yeah. So, here q star epsilon minus rho is equal to this product of epsilon alpha by 2 minus epsilon minus alpha by 2 alpha positive times product of epsilon minus alpha by 2 alpha positive. See, this is rho is half sum of positive roots. Therefore, I can write half running over this part sigma of so that is like the product, because in the group ring, I mean, so group ring alpha by 2 plus beta by 2 epsilon of that is, I mean, E of that is E of alpha by 2 into E of beta by 2. So, then I have to take product. So, this way, and therefore, this is equal to so this you see here alpha by 2 minus alpha by 2. So, for each alpha you take the corresponding pair, then you get product epsilon 0 minus this is 2 times. So, it is minus alpha, so alpha positive. Yeah. So, this is what we have. Okay, now the fourth thing is q star p equal to rho. So, q star p equal to epsilon rho. Yeah, so that the fourth thing will come from 1, 2 and 3. Let us see that. So, q star p star epsilon minus rho. So, this is same as so q star epsilon minus rho is this one. Star that p is product of f alpha by 1, product of alpha by 1. So, this is by 1 and this part is by 3. So, I am doing these two and then this separately, and this is same as this, yeah, but epsilon 0 there is another that one, the second one. So, this is product of epsilon 0 alpha positive, which is the value. This is by 2. So, 4 is done now. Okay. Now, let us come to the fifth one. W of q equal to W of product of epsilon q is alpha by 2 minus epsilon minus alpha by 2 alpha positive. So, this is same as product epsilon alpha by 2 minus epsilon minus alpha by 2 alpha positive W of alpha positive times product epsilon. So, this is a W, sorry, W of alpha by 2 minus W of alpha by 2 then epsilon. I write one more line, that will be more convenient. Alpha by 2 minus W of alpha by 2 alpha positive. Alpha W of alpha negative. See, I split into two sets. Positive roots for which W of alpha positive positive roots for which W of alpha negative. And here there is no problem, but here so the number, so for each positive root such that W of alpha is a negative root, that is on this part. So I just this is equal again. So this is no problem. Epsilon W of alpha by 2 pi minus epsilon minus W of alpha by 2 alpha positive W of alpha positive times, all right, or whatever star epsilon. So minus 1 power alpha, the number n alpha, just NW. I just explained what is the meaning of that. Epsilon minus W of alpha by 2 minus epsilon W of alpha by 2 alpha positive W of alpha negative, where NW number of positive roots such that W of alpha negative, this number. Okay, but that is same as that one. Yeah, I am using that that lemma. I am using the lemma. That number of NW equal to LW. I am using that lemma. I hope I can use that, right, this level. Okay. So, yeah, therefore, because these are, I have written everything starting with positive. W alpha by positive, here that is also positive. So, all are there and there is a bijection. So, that is why, so this is done. Only this, okay, we have time. So, the sixth part, so take any weight mu. So, if mu is not clearly, I mean, if mu is not less than or equal to lambda, clearly, I mean, this one is 0. The CH is a lambda of mu is 0, because of the maximal vector property, that every weight of the lambda has the property that mu less than or equal to lambda. So, if mu less than or equal to lambda, then use Poincare basis to, so we have to write, okay, to obtain for example, okay, a vector V of weight mu, which is equal to lambda minus some sigma m alpha. And suppose I take one sequence, fix a sequence m alpha positive of non-negative integers, then I take that thing. Then you can use that ordering of the basis. So, O alpha power m alpha positive to V lambda plus. So, this weight is lambda minus sigma m alpha positive, and clearly that is a, I use the Poincare basis, and that u minus n minus That's linearly independent. So they all, I mean, they have different, therefore they are all linearly independent. If you see one sequence, because a sequence, I write it in that order of the positive roots. So then they are all linearly independent. So for each partition, I give this thing. And conversely also, if you, any vector should be of this form. So that's a bijection. So this proves that this part. So if you take this number is precisely that number. And of course, this follows from the definition. How to, I mean, it's epsilon lambda is only lambda 1 at lambda, otherwise it is 0. So then you need to take mu minus lambda here and how many times you write. So that's so this part is okay therefore. Yeah, so we can stop here today, and then we will continue on tomorrow.